So thanks everyone for coming, avoiding like whatever free drinks you can get. There's lots of those still, I'm sure, don't worry. So I'm going to be talking about a new tool that was just pushed to GitHub, and it's really more a proof of concept, but it's supposed to take side channel power analysis and make it really easy and accessible. With one, the idea is to make this work on a lot of different devices to show you how easy power analysis can be. So I started a project, Chip Whisperer, which then has led me to this project as well. This is an extension of it. As part of that, I have a startup, New A Technology. So we do open source tools, we sell tools, we do trainings. One of the problems with open source, of course, is you can't git clone a PCB file as much as we would love to. So as a temporary fix for that, I brought a few of these tools with me, and we're just going to do the Mandalay Bay Insurance approved toss into the crowd. So I don't know who wants them. Look, we got one that way. Oh, crap. Okay, sure. Oh, no. And we'll do a far back. I don't know. Oh, disaster. All right. Cool. Thank you. Yay. At the same time, all right, there you go, git clone PCB. At the same time, so I recently started doing a little more research. As part of that, I'm with a university in Halifax, Dalhousie University. So I'll put this sort of advertisement out there if you're a student interested in doing a lot of deep dive into this research, like a master's or PhD, if that's something you might want to do. No comment on if you should or shouldn't. Feel free to talk to me. Find me. I'll be here until Saturday morning at DEF CON 2, so find me on Twitter or anything like that. All right, so into it. What are we looking for? We're looking for hardware acceleration in crypto. Specifically, I'm looking at AES. And this is interesting. It's used for a lot of stuff. It's used for firmware updates. It's used for securing magic money in wallets. It's used for all sorts of interesting things. And these devices all say, like, okay, they have AES, and the marketing people tell you it's the best in the world. You might want to validate that. You might be curious what that actually means, because there's ways to break it. So power analysis, there was a talk even showing how to do this at a distance just a few hours ago, so that's pretty cool. Has been well known since 1999 though. And in this example, I'm using it to break a Philips Hue smart light bulbs to recover their encryption keys. And it's relatively applicable. It's something you can do, and it's very fundamental. It happens because the power a device use actually changes a little bit with what data is going across internal data buses. So we have internal states that are affecting measurements we can take externally on the chip. And we can use this to break implementations of really secure devices. So we can break an implementation of AES or an implementation of RSA. I'm not saying RSA is broken, I'm not saying Adi Shamir screwed up somehow. I'm saying the engineers that do the implementations, they might have screwed up. But it's really fundamental. It's really, when it gets implemented in a design, this is where the problems happen. And that's what's really interesting to us. To exploit power analysis, there's a bunch of ways to do it. One way is that we have a model, and sort of most of them have this idea of some sort of fundamental model of there's secret data inside the chip I need to get out of the chip. And I'm going to make some assumptions regarding, when some secret key byte is some value, what the power measurement looks like. We could do that with, a template. We could record a whole bunch of data being processed with different encryption keys and figure out exactly what it might look like for every encryption key, every part of the encryption key. Or we can use the sort of easier way. We use some really basic models that have really sort of fundamental underlying assumptions. This method with these basic models is nice because we don't need to know a lot about any device. If you give me a device, it's running AES, that's kind of all I need to know to run some of these basic models on them. You don't need to do any sort of work ahead of time. And it's this basic attack that we've seen used in real life a few times. And this has been used to break, real products, real devices, to recover encryption keys, to demonstrate how they could be cloned. So it's far from just, I've chosen this on purpose. I've kind of chosen this method because when you look at what people have used for attacks, it's this kind of basic model. And this is known as correlation power analysis, or CPA attacks. And this is the only thing I'm really concentrating on this talk, is this specific version of that talk. So to do this, you need this model of the device. And if you look in a few papers, there's some like notes that they found these crazy models that they sort of found by coincidence, and it worked really well. That's the thing. It worked really well. It wasn't what they were expecting, but they found it. Great. So I want to improve that because, you know, the researcher shouldn't be testing all these models they're thinking up or anything like that. It seems like a silly problem. And it seems like it might be a good problem for machine learning. I tried that once. The year was 2003. I was in high school in my parents' basement working on a robot that was trying to use a neural network to drive. And it did a little bit worse than an if statement. But, you know, that seems to be kind of pretty good. So, and actually I tried it twice. The first time with BASIC on a micro. So that was, you know, we're kind of coming around back to like Python on micros and stuff. So maybe it'll be cool again. But I kind of gave up on that. It's actually a really pretty nice problem for machine learning. We have huge data sets for this. So actually Jasper is going to be talking about this later. So you're going to find out the smart way to do this tomorrow. We can make pretty big data sets because we control the device. The acquisition environment we control. The outcome's very well defined. You know, we get this key byte. This is a success. This is what we're trying to find. The main problems with machine learning is I didn't look at it since 2003, and people don't use BASIC anymore. The other problem with it is that we actually do know sometimes the underlying model, and we'd actually like to validate what that model is. So in our case, we know what the algorithm is, and we'd like to figure out where the problem's coming from, because that can help us fix the problem in the design. It does help us attack it, but it could also help us fix the problem. So the basic dumb method, the summary of it, is I take the algorithm, and if you look at AES, it has all these states, and we just say, well, we're just going to look at every state and just try all of them and combinations of them. And there's a lot, you know, it's not a simple problem to solve manually, but luckily, Amazon converts money into lots of cycles. And so we use money to cycles to solve our problem. And this is really what it is that it's sort of a tractable amount of problems. Like it takes, you know, a few minutes to run on a reasonable server, or if it's a complicated one, a few hours. It's far from a, you know, really prohibitive amount of computation that you might need. And so this was one of the ideas, is that why don't we just try everything, take our model, try everything, and see what we get? So the question is, what are we using to define this? You know, how do you know that it's a bad problem? How do you know it's a witch? And we're using test vector leakage assessment for this. It's based on the proposal. So there's a proposal on how you could validate if a device is secure or not at all, which really just answers the question, is this device secure? Not specifically how does the device leak? And it's really pretty straightforward. The quick explanation for it is, imagine you had a device, you want to know, hey, is this device secure? Can I figure out the encryption key from this device? If you could imagine encrypting a bunch of data with one secret key, encrypting a bunch of data with another secret key, the question might be, you know, could I tell which key was in use? If I gave you any random trace of the encryption, could I figure out what key was in use? So we can use these sort of questions, we can use statistics to answer. And they give us a value that has some confidence on how likely or unlikely the AES algorithm's a witch. So the results of this are a t-statistic we're using with two different types of tests. So the one on the left is the sort of classic test that was previously presented, which is giving you pass-fail type of testing. The one on the right is, which the tool can output. The one on the right is more interesting because basically we extend this model to figure out what specific state within it could be leaking. So what specific area are we seeing this problem from? This helps us figure out if a device is breakable, step one, and how to break it, step two, so we know it's a real problem. And then probably fix it, but I don't do that part. So this is supposed to say get on with it, which I don't think you need audio to know that if you've seen Monty Python. So I said I was going to do hardware crypto. I said I was going to break some micros, so let's do it. I've chosen some representative samples. I've basically chosen a few different micros that you might use for various tasks. Mostly Cortex M4. They're not secure devices, so they're not marked for like content delivery or in your credit card. Some of them find their way into special wallets anyway. You can take a look and see which ones get used. And it's not an attack specific to these micros. So I've talked to these companies about it, and they were often well aware about these attacks. They have people that do this type of work themselves. One of the problem is that customers aren't asking for protection against these attacks because they might not actually care about them or know about them. So the attack really exists because people misuse the crypto core. They take a device that shouldn't be used for really secure key storage, and they just use it anyway and say, that's fine. We'll just use that same key everywhere. Okay, that's enough of that. These are the devices. So STM32F415, a NXP Kinetis or Kinesis. Someone told me how to say that properly, and I'm not staying on brand, so I'm sorry. K24F, Espressif ESP32, Atmel SAM4L, or that should be microchip. Again, branding issues here. The test setup looks like this. So I'm using the same Chip Whisperer Lite on the left. This is just doing power measurement. So this is allowing me to measure power traces of a device. And then I have all these test boards with different chips that I've chosen. And so the test boards run an algorithm. I measure the power consumption and then run it through the tool to see what it comes up with. So the first one, the STM32F415, it has hardware crypto. It's a pretty powerful ARM core, Cortex M4. And the encryption itself, so I just have some of the traces to, if you wonder, like, what does it look like when we're looking at the leakage? The green line is the start of encryption based on some measurements from the tool. The red line is the end of encryption. So the middle part is the actual hardware crypto itself as the device is running. So what you see is this is a classic problem with hardware implementations. They basically save the AES state in a register, and they'll overwrite that state register as the algorithm progresses. So you get what is known as a state-to-state leakage, and it's Hamming distance because number of bits that are flipping, we can measure that. So you see that leakage is what the suggested model is. Performing the analysis gives you that they all leak at one point in time. Again, kind of what you expect with a hardware crypto. And with this basic attack, it's about 6,000 encryptions needed to recover the key. So if you had a device, you can cause it to do 6,000 encryption operations, and you can recover the AES key with almost 100% confidence. The next guy, Kinetis K24, Cortex M4 again, a bunch of different hardware crypto in it, including hardware AES. This one's a little different. So the best leakage was on the substitution box of AES, the S box. You saw a difference between the input data to it and the output data from it. So actually a little more odd for a pure hardware crypto implementation. The other thing with it is that, oh, so there's the power trace of it running the hardware crypto. So that looks kind of what you'd assume for hardware crypto. You see a lot of spikes related to each round. But the sort of interesting thing was that, now this figure's probably a little messy, but there's kind of 4 peaks. So it's not all lined up perfectly. There seems to be like 4 points in time where that S-box input-output is being used. So the implementation is a little different than expected, but it still results in a successful key recovery. So and that's about, in this case, 14,000 traces, so it's a little noisier. I'm using pretty basic Windows here, but you can see it's, we're talking still within the same order as the previous device. One of the other things that occasionally caught this tool is you could see stuff like ROM code. So some devices have ROM code that calls the hardware accelerator, or they provide a library that most people are using for talking to the hardware accelerator. And you can have issues like if you store the key in a register and you overwrite that key with controlled data, so either ciphertext that's known or the plain text or something like that, this gives you leakage that could actually be exploited. So some of these detections found that, which could be really useful in a real product where if you're just trying to recover a key, it's not the actual hardware accelerator causing the leakage, but some bad usage of it really made the side channel leakage a lot worse. The next device, Espressif ESP32. It's a really low-cost device. Has a lot of stuff in it for the cost. It's crazy. It has an AES accelerator anyway that can be used to decrypt external SPI flash to load data in as it's coming in. So this one just shows it was suggesting it indeed was going to be breakable, and it saw a Hamming weight of the S-box output, so relatively common leakage model. In this case, about 18,000 traces are needed to break. This wasn't looking at the boot usage, so this is using the device to encrypt or decrypt data. All of these, I tried to keep it as consistent as possible. You set up the device, do encryption or decryption, and you're able to recover the keys with this. So an interesting extension is to actually look at the device as it's booting, and if it's the same crypto core usage. The microchip SAM4L, this one's kind of cool because the hardware AES engine has countermeasures. So some of these vary with how well they work, as we'll see in a second. So it's a Cortex M4, it's running at 48 megahertz, so it's kind of a low power guy, but it's still got hardware AES, that's all we care about. And here's what the power trace looks like. So there's a middle section there that's actually running the AES algorithm itself, which is the core part of it. So when I first booted this chip up, which claimed to have countermeasures on, fully on, we saw the same sort of leakage as I saw from the STM device, which you wouldn't expect, basically. That was a little weird. And it turns out that there's a datasheet bug. So if you just look at the datasheet, it says when the device is up, everything's on, you don't have to do anything. It turns out there's an initialization step you have to do that's not documented at all in the datasheet, but so their library code, I eventually switched to using their library, which seemed to work, which it took a little while to figure it out, but when I contacted them to sort of go through this, they basically said, oh yeah, okay, that's the problem. So it's sort of interesting. So once you turn it on, it's basically jittering around the last few rounds. So the direct attack, I kind of used the same attack on all of them. It would stop that. So there might be more work to be done to fix that, or machine learning will probably save us and break it. You can ask Jasper that, buy him some beer. But what it found out basically is that some of the countermeasures don't do it. So there's an add noise countermeasure, for example, that didn't do anything, even when properly enabled. But more importantly, there is this datasheet bug that you might not find if you just relied on the pure, the datasheet and implemented. So that's the four of them. There's the fifth device. There's a device running ROM code in the white paper, just for speed. I haven't included it here. Basically, what you can see is that it's all pretty similar leakage amounts, 3,000 to 20,000 traces. But if you're using these in a product where you need to rely on the key storage and key protection, it's really important to understand that power analysis can, really quickly, really easily break these devices. And the point of selecting these was many of them I hadn't seen published before, a specific break on them. So some people might say like, okay, they haven't been talked about, so I'm sure they're fine. The other thing with the tool that's kind of interesting is that we can do some sort of automated testing of various libraries. So this one, what we have is like this kind of crazy diagram. And the top step, we have source code. We compile it with whatever compiler. So we have like IAR and GCC and everything like that. We take the binaries and program them onto different hardware. So I was using different Cortex M series devices was the objective, to see if there's differences in the Cortex M series. Put it on the platform, do the power analysis, and get these results. And so the results are kind of giving you pass-fail for different steps in the process if it's suggesting it might be breakable. So you can see a few things. You can see that, don't worry about the text. You can see the white paper for details. But basically for different options, some things seem leaky where other things aren't leaky. And depending on ROM or RAM tables for the lookups, the compiler, turning optimizations on or off, you saw differences. So if you just took a library that you said, okay, this has side channel countermeasures, we tested it, it's great. When you compile it later, or compile it for a different architecture, you may find things change a lot. So yeah, just testing for one device, even if it's in the same family, probably is insufficient. The other kind of interesting thing is that I didn't expect actually to find out is some of these also introduce timing attacks. And basically what it is that the flash lookup on the STM32F2 is done 128 bits at a time. Within this 128-bit lookup, if your same lookup is in that same sort of row, it's a little bit faster than if you go outside of it. So it's similar to a cache timing attack, but without the cache being enabled. So if you can totally disable the cache, you turn everything off you can, you always see this inconsistency. The only way basically is to switch to RAM tables or to always do a lookup back to some constant address, which you wouldn't really catch without hardware validation. Now, it is a little different than cache timing. It's not as clearly possible to exploit this. It does have some information, but because you can't clear the cache or anything like that, it's not as bad an attack as a classic cache timing attack. So yeah, that's sort of a quick overview of things that you can do with ChipWhisperer-Lint. And the point of this is that power analysis, please care. It's real. There's lots of talks now demonstrating it. And one of the points here is that, you know, it's not necessary to be doing lots of research to figure out if a new device is breakable or not. There might be a bit of research needed, but you can automate some of this sort of detection mechanisms. If you need to break, you know, a generic sort of crypto AES implementation, ChipWhisperer-Lint, which is published at this repo now, can help you sort of brute force some of these leakage models. And it's a pretty simple idea, so you know you can extend this to other algorithms really easily. And the other thing is to start looking at doing automated software testing. So if we do hardware in the loop testing, we can actually detect flaws coming up from specific compiler optimizations or architecture optimizations. So yeah, that's what I wanted to talk to you about today, to show you these demos, show you it's possible. And if there's any questions, I'm happy to take it. I think we have 2 minutes, 0 minutes? 3, okay, 3 minutes. So if there's 1 or 2 questions, yeah.
Hi. You skipped over one slide very quickly where you talked about the test setup and you had embed DLS in there. So I was wondering whether you had incorporated access to the hardware crypto into the embed DLS library and made that code available, or how did that fit in there? The slide was advancing so fast that I didn't.
For which slide, sorry?
Go back a little bit, one more.
This one?
Yes.
Yeah, so the embed TLS, so I was looking at the AES software. So specifically, I was curious about when people are building the software crypto libraries across different architectures. Okay. The hardware crypto changed, that's kind of a pretty, I'd expect that to change quite a bit. I was curious if you take a software crypto. So this is all with AES software build. So this demo is also online. It's linked if you want to try building them yourself or seeing all the build flags that were in use for it.
Okay. So that's in the same repository as?
It's linked to the repo. I just didn't, yeah. It's not in the repo because it's a bunch of files. So yeah, Jasper.
One tip and one question. So if you put the chip in water and if it floats, then you know whether it's a witch or not. The question is a bit more serious. Did you see when you look at different compiler options, were there particular ones that always led to more or less leakage, or particular compilers that led to more or less leakage?
No, not. I didn't really do too much work besides seeing there was differences. So I don't know. Yeah, offhand, I don't have a good answer. There was the ROM RAM table, so that was not so much the compiler as the embed TLS option. That tended to add a lot of differences. Between IAR and GCC, I don't think I saw much difference, which I think IAR wouldn't like me saying that, but.
Okay, thanks.
I don't know where we are, sorry.
Right.
I didn't see who was first, sorry.
It's okay, I'll get it next time.
Okay, we'll go this side.
All right. Can you go back to the slide where you introduced the 4 targets of evaluation?
1 second. This one?
Yeah. Okay, so there's one with a like a footnote. It's got an asterisk on it. Just scan forward slowly.
Like on the summary of the crypto.
Yeah, and it was.
It's probably the SAM4L because that one has the weird. This one or?
No. There it is.
Okay.
You had the responses. You said you contacted the manufacturers and you had the responses from them. Is that on here? Not speed optimized.
Oh no, that was earlier.
Yeah. Okay. Are you able to get to that slide fairly quickly? There was something on there that was a little bothersome. That
Was it the 1 week before?
no, not even that.
We're out of time.
Oh,
Okay.
here we go. Yeah. So this is not an attack specific to the micros. Nothing's more broken now.
I think we've actually run out of time.
Yeah.
So.